Hi everyone and welcome back. So today we're going to be talking about a specific class of differential equations called conservative systems. These are a particular type of the thing that we've been talking about, nonlinear systems, and it's a particular class that comes up quite often in applications. So we begin in this way. We begin with a differential equation that's second order. So y prime equals f of ty and y prime. And this is basically any second order nonlinear differential equation. We can convert these to systems if we want. We can convert them to first order systems in the ways that we've practiced. So let's suppose that in addition to this differential equation, there's also a function, h, with filler variables u and v, such that anytime we have a solution, y of t, for that differential equation up there, h of y of t, comma, y prime of t is a constant. So if we take our solution and we put y of t in for every u and y prime of t in for every v for a solution to the differential equation, the outcome from this function h will always be constant. It'll be the same for any different t value you put in there. If you pick a different solution y of t, of course, you might get a different constant, but along the solution trajectory, this h of t is constant. If that's the case, then we say that h is a conserved quantity. And that makes sense, right? Along your solution, so for as long as this system is playing out in time, this quantity h will be constant. It will be conserved. And when there is a conserved quantity for your differential equation, we say that the differential equation has a conservation law. Now, you may have heard of conservation laws before in the context of physics or chemistry or other settings like that. So some examples. You might have heard of the conservation of mass or the conservation of energy. That's the idea that in a closed system, the total amount of energy cannot change or the total mass cannot change. Although if we're being really correct, these are actually part of the same larger conservation law, the conservation of mass energy. We have to put them together because it turns out that you can convert between mass and energy, right? According to the equation E equals mc squared. So the energy is equal to the mass times the speed of light squared, which tells us how much energy is created by annihilating some amount of mass. That doesn't usually happen in your system, so you don't have to worry about it. So you can treat mass and energy as being conserved separately because there's no transfer between them. Anyway, that's beside the point. Okay. You might also have heard of conservation of momentum, either linear or angular momentum, the conservation of electrical charge, or conservation of probability in a mathematical setting. And there are many other kinds of conservation laws. In each of these cases, a conservation law gives a quantity that, once a system has been set in motion, does not change. Knowing the existence of a conserved quantity can make the system easier to understand, and it also restricts the realm of possible behaviors, which is useful if you're trying to classify the kinds of things that can happen or control a system. Knowing the conservation law will help you do that. And often if you see that the behavior of a system is constrained, it makes you suspect that there is a conservation law in work. And then you have to go out and find it, right? Figure out what the conservation law is. So when we talk about these conservation laws, some obvious questions should occur to us at once. The first one is, how can we recognize when an equation or system has a conservation law, when that equation or system of equations is, as they say, conservative? And how do we know what the conservation law is if we know that it's existing? And then once we have one, what do we do with it? Well, let's begin with an example, and this will incorporate some of the things that we've seen before. Suppose that we have an autonomous equation, so t is not explicitly in the equation, of the form y double prime plus f of y is equal to 0. So we've seen examples of this before. Undamped spring, m y prime prime plus ky equals m. That would be y double prime plus k over my equals 0. Or a frictionless pendulum, we've seen theta prime prime plus g over L sine theta equals 0. Now, it turns out that any equation that has this form, and there are many equations that have that form, is conservative, has a conservation law. How can we figure that out? Well, we do a little bit of clever calculating. We take this equation. Well, first of all, just for notation, capital F of y is going to be the antiderivative of little f of y with respect to y. And we'll figure out what the conservation law is. So y double prime plus f of y equals 0. We're going to multiply through that equation by y prime. So y prime times y double prime plus f of y times y prime equals 0. And now integrate both sides with respect to t. And so we get this integral here. Now, what we see here is if we are very careful, you can do a substitution, u equals y prime, or you can think about this using the chain rule, but you should get that the antiderivative of the first part is 1/2 y prime squared, and the antiderivative of the second part is capital F of y, and then finally the antiderivative of 0 is a constant. So we get this quantity that is a function of y prime and y for our solution, and that is constant. So this is a conserved quantity. H of uv is equal to f of u plus 1/2 v squared. All right, reasonable enough. Of course, not all equations have this form, and yet other things do have conservation laws, so we're going to have a way of recognizing them. So we'll get more to that in a little bit. But first, let's look at how this kind of system plays out in the phase plane, which we've talked about last time. So first of all, let's take this equation that we have, y prime plus f of y equals 0, and convert it to a system of two differential equations. So I'm going to do that by introducing some new variables. Let's call y1 will just be equal to y, and y2 will be equal to y prime. So now we can get differential equations for these guys. y1 prime is equal to, well, it's equal to y prime, which is the same as y2. So y1 prime equals y2. Got a little bit of a mess there. All right, so that's one equation. And then y2 prime is equal to y double prime. And from our original differential equation, we know y double prime is equal to negative f of y, which is negative f of y1. So our system is y1 prime equals y2, y2 prime equals negative f of y1. Now this subscript stuff is pretty inconvenient, so we're going to rewrite it. I'm actually going to take my y1 and call it x. I'm going to take my y2 and call it y. I know that's an abusive notation because y was already used before, but we're going to do it anyway, and that will give us the system written in this form. X prime is equal to y, and y prime equals minus f of x. All right, so that's the system that we're going to be looking at, or that we have been looking at up to now. We know that it's conservative, and that its conservation law is 1/2 y squared plus f of y equals c. Now, if you recall, in the phase plane, the solution curves are these curves, are just curves in the plane, in the xy plane. But also this equation, this conservation law that we have here, also defines curves in the xy plane. For any constant, the set of points x and y that satisfy this equation will form some kind of set in that plane. And solutions also have to follow this because that's what the conservation law says, that solutions obey this equation. So it turns out that every solution will correspond to some particular value of c, right? We could just put in an initial value for x and y, and that'll tell us what c is. And then the solutions have to maintain that value of c for the quantity 1/2 y squared plus f of x. So solution curves will correspond with what are called level curves of this function h. So you might recall that from multivariable calculus, right? This is a concept from level curves. So the most common example of level curves are topographical maps, right? You have a function of x and y that gives you the elevation, and the level curves are the topo lines, the lines of all the places with a particular height, right? You pick a constant, which is an altitude or a height, and the curves you get are the topographical lines. That's the same thing we're doing here. Basically, this conservative quantity, or this conserved quantity, this conservation law gives us something that will let us draw curves in the phase plane, and those phase plane lines or curves correspond with the solution curves. So we know exactly how the system behaves. That's one of the big ways that conservation laws help us understand the behavior of solutions of differential equations. So let's look at a particular example. Let's go back to our example of the frictionless pendulum. So remember we had an equation for the frictionless pendulum. It said that theta double prime plus g over L sine theta is equal to 0. So this has the right form if we just change our variable names. So if we're changing our variable names, so x is the angular position, theta, y is the angular velocity, theta prime. If we do that, we get the system x prime equals y, and y prime equals minus sine x. So what is the conservation law for this? Well, our rule said that it would be 1/2 y squared plus the antiderivative of f, which in this case is sine x dx. So that's 1/2 y squared minus cosine x. And that will have to be equal to a constant. Or we could write it as 1/2 y squared equals c plus cosine x. It makes no difference, right? So this is the conservation law for this system. So if we can figure out what level curves of this look like, we'll have a picture of the phase plane. So let's give it a go. What can we do? Well, the graph is going to look different for different values of c. And we have to think a bit hard about this. The main thing that we have to pay attention to is the function cosine x. So the left-hand side, as we've written it here, is 1/2 y squared. So we need the right-hand side to be positive to have solutions. Cosine x has values between -1 and 1. So to make this positive, that'll only happen for certain values of c. So we have to break it down kind of case by case. And that's what I'm going to do now. So one case is if c is less than 0. Sorry, not less than 0. If c is less than -1, then 1/2 y squared equals c plus cosine x will have no solutions. Why doesn't it have solutions? Well, in that case, c is less than -1. The biggest that cosine x ever is 1, so the right-hand side will be negative. And then we have a negative number equals a square, so that can't happen. So we get no solutions there, no curves. So there's just nothing happening there. If, on the other hand, c is equal to -1, then the right-hand side is equal to 0 sometimes. It's only equal to 0 where cosine of x is equal to +1. So that only happens when x is 2 pi. Oh, sorry, 2 pi? Let me think. Yeah, cosine of x will be 1 only when x is equal to some multiple of 2 pi. Right? So we get, in this case, the so-called level curves are just points, 2 pi k, and y is 0 in that case, right? Because y is 1/2 y squared is equal to the right-hand side, which is 0, so y equals 0. So that's one set of level curves that we could have. Okay, now what if c is between -1 and 1? So in that case, you have the cosine curve has been moved up or down by a number between -1 and 1, and we're going to see that the right-hand side is sometimes positive and sometimes negative. So on the values of x for which it's positive, we'll have a corresponding y value. So when the right-hand side is positive, or 0, we get that y will be equal to plus or minus the square root of 2 times c plus cosine x. All right, so we'll get two different y values for every x value, but we'll get a positive thing here, multiply it by 2, take the square root, now we've got ourselves the y value. All right, and then finally, if c is greater than or equal to 1, the right-hand side is always positive, or non-negative, we'll say positive. So for all x, y is equal to plus or minus the square root of 2 times c plus cosine x. All right then, a fair number of things that happen, and you can try to figure out what those curves look like. One thing that you'll notice is that every x value has the plus and minus of the y value, so we should expect symmetry in these curves around the x-axis, because every point xy has a corresponding x minus y that goes with it. So we're going to have some symmetry going on here. In fact, there's lots of symmetry involved. So let's take a look at what these curves will look like. Here is the phase plane for this system, or the system of equations, and we have a lot going on here. Each of the blue curves here that I've drawn in is a solution curve or a level curve of the conservation law, and the red dots are equilibria. So this one here is 0, 0, and what you see is that, so basically that red dot corresponds to c equals -1. These circles, these closed circles, correspond to c values between -1 and 1. And in fact, we get several of them. So this circle here will correspond with another circle of the same size over here, and every other equilibrium that we have will correspond to a circle like that. And so then those are the curves with c between -1 and 1. When c equals 1, we get these curves. There's a curve that connects those two equilibria. That was a very bad drawing job. But we get these things called heteroclinic orbits, things that connect one equilibrium with another equilibrium. And then finally, when c gets larger, we have these solutions that look like this, right? This is the ones where for all x values they exist. These other ones, you're going to have these gaps. We have a circle, and then a gap, and then another circle in the level curve. So it doesn't exist for all x. These ones, they exist for all x. So what on earth is going on here? Well, there's a lot that's going on. Remember, this is representing a pendulum, right? So let's just get a picture of a pendulum to keep us in mind of what's going on. A very simple drawing of a pendulum. And x is measuring this angle here, and this thing can move, right, from side to side. So the x coordinates here represent the position of the pendulum, also known as its angle, right? When it's equal to 0, like at the equilibrium right here, that's when the pendulum is hanging straight down. When we get to over here to pi, that represents when the pendulum is actually standing straight up. And then we have every possible thing in between. In the vertical direction, we have the velocity, right? Because remember, y is equal to theta prime. X is equal to theta. So this is the angular velocity of the pendulum. It's telling us how fast it's swinging back and forth, all right? So it's interesting. And we also see I've drawn in the direction field. So we have the arrows telling us that up here, things move in this direction. Down here, they move in this direction. Why is that? So what does this represent? Well, what you can imagine is, imagine that you're on one of these closed orbits in here. This circle has to represent some kind of motion of the pendulum. And what motion is that? Well, consider what's happening at this point right here. At this point, that's the highest x value that this curve will ever achieve. So that would mean that the pendulum is as far to the right as it's ever going to be. And then from there, the arrows say we proceed this way. So the position, x, is moving to the left. So it gets smaller. It goes from being out here and moves this way. What happens to the velocity then? Well, the velocity is getting larger. It's picking up momentum, picking up speed. As it goes this way, it gets a more negative, right? It's going down from 0, more negative velocity. Negative velocity corresponds with moving to the left. So it's moving to the left faster and faster. Here, at this point, x is equal to 0. That means that the pendulum is hanging straight down. But it's not still. It has a velocity with it, so it will keep going this way till it reaches the point on the far left. I think I've changed circles in there somewhere. But in any case, it gets to the farthest left it's going to be. And at that point, it changes direction. It starts moving in this direction again, right? When it does that, now it has a positive momentum. It's heading back to the right, and the position x is moving from the negative to the positive. The position is getting higher, so it goes higher and higher. So this would represent, all of these closed orbits will represent systems where the pendulum is swinging back and forth, back and forth, back and forth. And since there's no friction, it'll just keep doing that forever. It'll just keep going around this circle again and again and again and again. But that doesn't represent the pendulum going around and around and around. It represents the pendulum going back and forth. If you start at the equilibrium, that represents the pendulum hanging down with no velocity, so it just stays there forever. What's going on up here? What are these things? Well, this is what happens with a frictionless pendulum. If you give it so much velocity, so much energy, right? You pick a C value that's so high, representing the total energy in the system, that it just goes around and around and around and around. It just keeps circling. It has no friction, so there's nothing to stop it from keeping going around and around forever. So the velocity is positive at all times. It's always moving in the same direction. And the angle, well, it goes to 0, then it goes to 2 pi, then it goes to 4 pi, and so on. And those are really representing the same positions in physical space, but in the phase plane we see them basically counting how many times has the thing gone around the circle. And then the same thing happens down here, but in the opposite direction. This represents giving it velocity in the other direction. You just push it the other way. So the ones up top would represent going around clockwise. The ones in the bottom would represent going around counterclockwise. And then finally, we have these very weird homoclinic or heteroclinic orbits that I was telling you about, where you start at minus pi, or say you start at pi, and then you give it a push, and it goes like this, and then ends up here. What is going on there? Well, that is a very strange set of occurrences that you can't really do in practice, but this would represent starting a pendulum at the top and giving it just the right bump, just the right amount of energy, so that it would go around, and then get back to the top and balance again. Is that ever going to happen for real? Of course that's not going to happen for real. In the real system, there's friction that changes things. There's all kinds of things going on, and you just couldn't match it that well. And also the interesting thing is that the amount of time it takes to follow that path from here to here is infinite. It'll just keep approaching, kind of moving in that direction, but never quite getting there. So a lot of interesting stuff going on here. The main thing to take away, in addition to like being able to look at a phase plane and interpret physically what it means, what does it mean about the behavior of solutions, the main thing is to look at this and see this is also the same as taking a function 1/2 y squared minus cosine of x and plotting its level curves, picking c values and then plotting those things. You get these